Today we are going to discuss about the antibacterials. So antibacterials means which kills the bacteria. Okay. So here the antibacterials are the chemicals used for the treatment of certain disease caused by the bacterial infections. For example, here the sulfanilamide and its related compounds known as sulfur drugs here. So these are the very effective drugs. Sulfur drugs are the very effective drugs to treat the bacterial infections like pneumonia. Okay, we know the various types of bacterial infections like pneumonia. Okay, and some throat infections and eye infection, meningitis. Okay, all these are this some kind of bacterial infections. So under this bacterial antibacterial drugs, we have various types of drugs. The most probably here is the penicillins are the most frequently used drug as antibacterial, and tetracyclines also used as antibacterial, uh, and means they will combat bacterial infections here. So we are going to know more about this sulfur drugs. Here the Domac he was discovered the a red dye stuff, frantosil, where the frantosil is a 2,4 diamino azobenzene 4 sulfonamide. Okay, this is the frantosil where it is the prodrug. It is acting as a prodrug. Prodrug means it is not having any pharmacological activity before consuming the drug here. So when this drug is taken, right, when this drug is administered, then some reactions will be takes place due to enzymatic reactions or the reactions with some acids present in the stomach. So it is converting into the active drug compound. These are called as the prodrugs here. And we'll see this the structure of this frantosil. Here is a frantosil. Right? So here is a frantosil drug where it is having the azo, right? Diazo linkase. So this sulfanilamide nothing but here is a para-amino benzyl sulfonamide derivatives. They have a great antibacterial activity, and sulfanilamide itself is active against the infections caused by the streptococci and gonococci and pneumococci. Means these are the various types of bacteria here: streptococcus, nanococcus, gonococcus, and pneumococcus. These are the various types of the bacteria here. Okay, and the greatest danger with the sulfonamide is the crystal formation of acetylated sulfonamide in the kidney. So this is one of the adverse effect with these sulfonamides here. So, the more soluble sulfonamide drugs have been developed here. Means some the sulfonamide analogs are developed. So in that analogs, we have some examples like sulfadiazine and pyrimidine here, nucleus which is present on the sulfamido-nitrogen atom, and the activity and mode of action. Here, the solubility of these sulfonamides and their protein binding nature and the pathway metabolism and the mechanism of elimination that determine the toxicity. So we know that any drug, the active compound, okay, the active drug must satisfy the ADME properties here, where the ADME nothing but here here is absorption Okay, distribution, metabolism, and excretion. Right? So to improve all these activities like ADME properties, so we are prepared some analogs. Uh, in that analogs, we have all these sulfur diazenes, and where with the which is contains your pyrimidine nucleus here. Yes, so we go in detail about the sulfur diazine. So here is a sulfur diazine structure where its chemical name is sulfur diazine. Uh, Chemical name is the 4-amino N2 pyrimidal benzene sulfonamide. So with the molecular formula, you can see that there are 10 carbons are there, C10H10, N4O2S, where it is having the one amino group here and one benzene, diazine ring, and one aromatic benzene ring here. So it is a crystalline compound. If you see that the physical properties of this sulfur diazine, where it is a crystalline solid compound here, and its melting point around 252 to 260 degrees Celsius, and it is used as antibacterial, which is used to remove the other decrease to treat the bacterial infections caused by several bacteria like Bacillus, uh, Clostridium, and Streptococcus, Gonococcus, plague. So all these are the various types of bacterial infections which is cured by your sulfadiazine. And it is a drug of choice in a number of infections, including pneumonia here and influenza also. And obviously, most means all the drugs are having its own some of the a few of these side effects like toxic reactions here. So here the sulfadiazine also having a little bit of toxic reactions here. Here the sulfadiazine it can be the prepared means where the synthesis of this sulfadiazine. So you can see the sulfadiazine it can be synthesized by the condensation of para-ester-aminobenzene sulfonyl chloride. Here is a where you can see this 7. It is a para-acetyl amino benzene sulfonyl chloride. When it is treated with your 2-amino pyrimidine, right? So 2-amino pyrimidine here, uh, and then you get some the intermediate compound, and followed by the hydrolysis. Upon hydrolysis, so you will get some intermediate compound where the para-acyl aminobenzene sulfonyl chloride. It is a intermediate compound which is obtained due to this reaction, and it is synthesized by the sulfonation of acetonylide with chlorosulfonic acid. Okay. Okay. So next, that analog sulfonamide analog is sulfamethoxazole. Sulfamethoxazole. So where it is contained the uh, right. So where it is sulfonamide derivative, and it is containing one oxazole ring, 5-membered oxazole ring, and its chemical name is the 4-amino N5-methyl 3 isoxazole benzene sulfonamide, and the molecular formula of this sulfur methoxazole is C10H11 N3O3S here. And the physical properties of this particular sulfur methoxazole is it is a crystalline powder, and the melting point it's around 170 to 173 degrees Celsius here, and it is used as a uh, antibacterial, especially in the with the chronic urinary tract infections. And this the synthesis of this sulfamethoxazole, it can be synthesized by the condensation reaction of your 3-amino 5-methyl and para-acetyl aminobenzene sulfonyl chloride, where this the moiety, the seventh moiety here, where it is condensed with this particular 3-amino 5-methyl and the para-acetyl aminobenzene sulfonyl chloride. And finally, by doing the hydrolysis here, so in the presence of pyridine, we are getting this intermediate compound. And finally, by doing the hydrolysis, where it is giving you a sulfur methoxazole here. So the intermediate, like 3-amino 5-methyl isoxazole, it can be prepared, right? Here the intermediate can be prepared by the reaction of dimethoxazole light and the acetone and hydroxylamine hydrochloride here. So the resulting methyl isoxazole recarboxylate, which is treated further to obtain the corresponding amide derivative here. Then finally we'll get this particular 5-methyl oxazole 3-carboxamide here, and which is further it is subjected to the Hofmann reaction. You know the Hofmann reaction here, where the formation of amide to amine formation is a Hofmann reaction, and which is by treating it with sodium hypochlorite to get the required intermediate. So the mechanism of this reaction is uncertain, but the sequence may be even followed here. So you can see the synthesis of this particular intermediate compound. Here you see this particular right here the ester compound, where it is going to react with this particular hydroxylamine hydrochloride, and where this is the unsaturated alcohol. In the presence of base, it is going to cyclize, and we are getting this particular oxazole derivative here. And by removal of 2 moles of water, where we are getting this particular ester cyclic oxazole ester derivative. And further treating with ammonia. Okay, so further treating with ammonia, where this particular ester is converting into amide here. And finally, by treating with sodium hypochlorite, so it is giving your oxazole methyl amino oxazole derivative, intermediate compound. And next analog, sulfonamide analog is trimethoprim. Trimethoprim. This is also one of the antibacterial drug. Here is a trimethoprim is its chemical name is 5 3, 4, 5. Trimethoxy phenyl methyl 2, 4. Pyrimidine diamine. This is the structure of your trimethoprim here, and it is a bitter crystalline compound. So this is also one of the solid compound, and its melting point is around 199 to 203 degrees Celsius. And molecular formula of this trimethoprim is C14H18 N4O3. And this belongs to 2,4 diaminopyrimidine type of heterocyclic compound, because you see this is having the one benzene ring, right? The trimethoxy benzene moiety, which is connected with the CH2, CH2 bridge to this particular diazine, okay, dimethyl diazine ring. So it is heterocyclic compound, and it is having a effective anti-malarial and antibacterial activity. So this trimethoprim also acting as an anti-malarial agent, uh, and this is also acting as your antibacterial agent here. And the synthesis of this particular trimethoprim is done by using this particular sulfamethoxazole, right? So here you see where this the heterocyclic compound when it is treated with acryl nitrile, right? So where the side chain formation is takes place, then trimethoxyl benzaldehyde, right? So when it is going to condense with this particular oxazole derivative in the presence of sodium methoxide, so we are getting this intermediate compound here. And finally, by introduction of this particular the side chain, so we are getting this particular trimethoprim. And this drug, where the trimethoprim with combination with sulfamethoxazole in 1:4 ratio is used in the formation of bacterium and spectrum. So it is very effective in the treatment of chronic bronchitis and other respiratory tract infections and some chronic urinary tract infections here, right? Generally, the combination, right? So when this trimethoprim is combined with the sulfamethoxazole in 1:4 ratio, generally this combination, the drug combination, we call the drug synergium. Okay, so we call this the drug synergium here. Drug synergium means when the combined therapy, okay, the combined therapy, when the two or three, right, two or the more than two drugs are combined, and where it is used to treat some chronic diseases here. So here, this particular trimethoprim is combined with the sulfamethoxazole in 1:4 ratio to treat various chronic diseases like chronic bronchitis and respiratory tract infections and some chronic urinary tract infections here. The components of this combination drug, it is acts sequentially interfering with the metabolism of folic acid in the microorganisms here. So you know the folic acid which prepares the DNA. Yeah. So the drug reduces also the development of bacterial resistance and the synthesis of this trimethoprim. So it can be prepared by the condensation of 3,4,5 trimethoxy benzaldehyde with the intermediate morpholino pronitrile here. And then finally the addition of morpholin to acrylonitrile, it produces the morpholin propionitrile. And this particular morpholin propionitrile intermediate, it is condensed with the trimethoxy benzaldehyde in the presence of sodium methoxide and the aniline to give the 2,3,4,5 trimethoxybenzene 3 aniline pro 3 enyl nitrile. Nitrile nothing but the cyanide. Okay, so this will react with the guanidine nitrate to produce your trimethoprim. So finally, by treating with guanidine nitrate, so it is giving your trimethoprim here. Guanidine nitrate. Okay, yes. Next, the antibiotics. So, yes. So here the development of antibiotic drugs is one of the major advances in the chemotherapy here. So the introduction of the antibiotics, it has not only the influence the practice of medicine, but also finds applications in the animal nutrition agriculture and food processing industries here. And here the diseases brought it by the incurable a century ago have been treated successfully with antibiotics here, and it is used to treat various chronic diseases like childhood pneumonia, okay, and typhoid and uh, typhus fever and typhus fever and plague, cholera, tuberculosis, and some other infectious diseases caused by the bacteria and some fungus and protozoans here. Okay. So in 1938, where the and Chain, Florey and Chain and their colleagues, they were invented the chemotherapeutic potentialities of the enzyme lysosome here. So this enzyme has a property of lysing bacteria in vitro. In vitro nothing but where the synthesis or the preparation done in the laboratory or in the test tube here. We have the in vivo and in vitro methods, where the in vivo method, which is takes place in the inside the body, inside living organism. In vitro is the preparation or the synthesis or the development is done in the uh, test tube or in the laboratory here, artificial. Right. So they are isolated, they prepared and synthesized and isolated the penicillin here. It is isolated by the Alexander Fleming. You know that Alexander Fleming is one of the famous microbiologist here, and he was discovered the penicillin by accidentally. Generally, the penicillin is invented by accidentally here, like Alexander Fleming. Okay, when he was doing a bacterial culture experiment. Okay, so unexpectedly, accidentally or unexpectedly, he was invented. Generally, we call this unexpected invention of drug is called the serendipity of drug. Serendipity of drug means the accidental invention of the drug. Okay. Then the Florey and Chain, they were synthesized and uh, they were invented the structure of this particular penicillin. And various antibiotics which are developed in by their years, names and year here. You see, there is an antibiotic and year of discovery where the penicillin, so it is 1929, and streptomycin, where it is invented in the 1944, and chlorophenol 1947, and chlorotetracycline in 1948, and oxytetracycline 1950. The tetracyclines are synthesized and discovered in the 1953 here. Yes. Right. Here the antibiotics, they have very gently in their chemical structure, and they comprise carbohydrates, polypeptides, polyketides, etc. here. And the antimicrobial action of this antibiotic is selective, and some organisms are affected by these antibiotics and others are not affected, and some only to limited to degree here. And the mode of action and bacterial resistance. You see this antibiotics, generally they are largely bacteriostatic agents here. And they inhibit the growth of selective organisms without destroying them. And some also have marked bacterial or the bacteriostatic properties. they act upon the bacteria and increasing with their capacity to absorb and as accumulate that nutrients, also synthesize cell substances here. Yeah. So next we are moving to these penicillins. So in 1929, Alexander Fleming, he was found the microorganism known as Penicillium notatum inhibits growth and multiplication of these certain bacteria. At this observation of antibiosis means where the anti say against here, biosis means life of Penicillin notatum. So it is led Florey and his colleagues to discover the medical potentiality of the organism. And they suggest that the bacterial activity of the organism, it is due to the presence of a group of organic compounds. We call this the penicillins here. And the isolation of penicillins, how to isolate. So here you know that the penicillins are produced commercially by fermentation process. Various cultural methods have been developed for the production of penicillins on a large scale. And one of such method is a submerged culture method. And here we see the various penicillins, types of penicillins here. Here is a penicillin F, where its chemical name is pent-2 uh, enyl penicillin, and its side chain. Here is a penicillin structure where so this is the where the thio right here is the sulfur, one of the sulfur atom is in the 5-member ring. The sulfur atom is there, and nitrogen also the part of the heterocyclic ring 5-member, and where it is having that amide. Okay, so amide the beta lactam, we call this the beta lactam ring, means the moiety, and where this amides NHCOR. Here the in place of R, by substituting the various substituents, we have the different penicillins, where penicillin F is having the side chain with CS2, CS double bond CS and the ethyl. And next penicillin G, we call this a benzyl penicillin, where the side chain is substituted with the benzyl group here, CS2. Next, N-amyl penicillin, where its side chain is having that with amyl nothing but the 5. Okay, so 5 carbons. So it is having the 5 carbons on in place of R. And next, N-heptyl penicillin, penicillin K. The name for this is penicillin K. And phenoxymethyl penicillin, this is penicillin V. And para-hydroxybenzyl penicillin, where is the penicillin X here. Okay, so these are the various structures of the different penicillins here. And this is the core structure of this penicillin, where it is having the beta lactam ring. Right. So, and you see this is a very effective against gram positive bacteria and not against other microorganisms. So generally here the bacteria are two types, where the gram positive and gram negative. And this difference, gram positive and gram negative, is differentiated based on their cell wall structure here, where the gram positive is having the simpler cell wall structure because it is having only uni only one layer here. Okay, and where this gram negative bacteria, it is having the by polysaccharide chains here. So it is somewhat complex here, where the gram-negative bacteria cell wall is very complex nature. So here the penicillins are very effective against the gram-negative bacteria, and it is not against other microorganisms. So it is called the narrow spectrum antibiotics. We call this the BSAB. Okay, BSAB, nothing but the broad spectrum antibacterial, like chlorophymical and tetracyclines. These are active, effective against the wide variety of organisms. Okay, so but the penicillins are not. It is a BSAB, means broad spectrum of antibiotics. It is narrow spectrum of antibiotic drug because it is not active against the. It is only active against gram-negative bacteria, but not active against other things here. And penicillins have proved to be very effective for the treatment of pneumonia and diphtheria, scarlet fever, and childbirth fever, rheumatic fever, and wound infections, gonorrhea. Okay, so all these are the diseases which are cured by your penicillins here. Next, streptomycin. This is one of the antibiotic here, which is discovered by Waxman. The Waxman scientist, he was discovered the streptomycin in 1944, and the structure of this streptomycin is elucidated in 1948. Okay, and this streptomycin was isolated from the cultures of Streptomyces griseis here. And general the production and isolation, you see that with the manufacture of streptomycin, it is surface culture method was first employed, but it is soon replaced by the submerged culture method, as it is in the penicillin. In addition to other constitute the cultural medium, so it must contain the protein materials such as soya bean meal and cotton seed meal for the better growth of this organism. And the requirement for this, where it is incubated at 25 degrees centigrade for 3 days here. And this during this process, the antifoaming agent is added to this medium, and sterile acetylation is implied, means sterile. Okay, where to make that back means other microbes, removal of the microbes, the sterile. Yeah. And the early stage of growth, Streptomyces griseis is susceptible for the process here. And during that fermentation, the reaction medium changes from acidic to basic state here, and the point of highest alkalinity, that is pH 8.2 to 8.6 here. It's correspond to the highest streptomycin production, where you need to maintain that basic medium alkalinity. And the yield of this streptomycin can be increased by irradiating this culture solution by X-rays or the UV light here. Yes. So after fermentation, the mycelium and other waste products are separated by this filtration, and streptomycin is recovered from this filtrate either by absorption or charcoal on the base exchange resins and elution with this dilute aqueous or the ethanolic mineral acid. And this the properties of this particular streptomycin structure is, you see this the streptomycin is colorless solid. The physical properties, if you observe the physical properties, generally this streptomycin is colorless solid compound here, and it is a strong base because it is contains the, you see this structure of this streptomycin. Yeah, so it is having that nitrogen. So obviously it is a basic nature. It is a strong base here, and it is soluble in water, and also having the lever rotator because it is a chiral derivative. So it is having the optical rotation, that is lever rotatory. We know that the optical rotation is dextrorotatory and lever rotatory. So this particular streptomycin is a lever rotatory derivative compound here, and it's the molecule of streptomycin is built up for 3 units here. You see the 3 units are present in the streptomycin. One is a streptose here, and the second unit is N-methyl L-glucosamine, and the third unit is streptidine. So these are three units. It is combination of three units here. Okay, here is a two six-member ring, one five-member ring. Okay, here the unit one and two together is known as the streptosamine, and the streptose unit is neither solved from the degradation products of streptomycin nor synthesized, and its structure is derived from the reactions of streptomycin. And application of this particular streptomycin, generally you know that the streptomycin, it is active against gram negative bacteria, and it is highly encouraging since penicillin and streptomycin drugs are cheaply effective against gram negative bacteria and gram positive bacteria. It is a broad spectrum antibiotic here. And the streptomycin is specially employed for the treatment of tuberculosis here. And it has also used in the treatment of bronchi, plague, and influenza, meningitis. Okay, so meningitis means eye infections here. And the some adverse effect also there, like other drugs. This is also streptomycin is having some adverse effect. So that adverse effect is where it is having irreversible deafness. Sorry, deafness here. Next, chlorophenicol. Chlorophenicol. It is isolated, independent by the research group of uh, Erich and Carter. Erich and Carters, and generally the trade name. Yeah, the trade name of this chlorophenicol, it is chlorophenicol is chloromycetin. Okay, chloromycetin, and chlorophenicol is it is produced by an organism called the Streptomyces venizulae, and this type of antimycetis is obtained from the uh, soil sample near Venezuela. Okay, and this is the very simplest antibiotic for which practical synthesis have been devised here, and it is originally prepared by this fermentation process. So all these antibiotics here prepared by the fermentation process only, like streptomycin, penicillins, and chlorophenicol here. Next, the synthesis of this chlorophenicol is synthesized by using this paranitrohistophenone uh, when it underwent the bromination reaction. So we get the paranitro-bromohistophenone where the bromo substitution is takes place, and which on reaction with the hexamethylene tetraamine, which yields for this complex where you get this intermediate compound here. And this intermediate complex compound is hydrolyzed to paranitroamino estophenone hydrochloride. Next, this amino group is acetylated with acetic anhydride to give acetominophenone. So, which is on treatment with the formylation reaction or the formaldehyde undergoes hydroxymethylation and forms the paranitro 1-acetamido 2-hydroxy propiophenone. So this is the sequence of this reaction where it is undergoing some bromination followed by this side chain introduction here, and followed by the reaction treatment with this HCl where the yeah. Okay, and acetylation reaction. Here the acetylation in the presence of sodium acetate and acetic anhydride, and we get this acetyl derivative. Finally, by treating with this formaldehyde in the aqueous sodium bicarbonate, we are getting this uh, attachment of means conversion of this primary alcohol, right? And then we get two isomers here, trio and erythro. And by doing that resolution method, okay, resolution nothing but the separation of isomers. So we'll separate the D3O isomer. And this trio isomer will undergoes the uh, treating with this particular chloroester, and it is finally giving you a chloromycetin or chlorophenicol. Yes. And the physical properties of this phenicol, where it is colorless neutral solid compound, and it is bitter in taste, and it is taken orally. So you know that we have two administration methods. Administration methods. One is oral and intravenous here. So it can be chlorophenical is taken orally, and orally as well as the uh, okay, orally in the form of capsules here. And the applications of this chlorophymical is generally it is active against variety of pathogenic organisms, which are those which are causing the typhoid fever, bacillary, the dysentery, urinary tract infections, respiratory infections, ocular and optic infections, like rickets infections. Yeah. So all these are the uh, treatment okay diseases which is used to treat the okay to, which is used to this particular chlorophynical right. Next, the tetracyclines. So here the tetracycline nothing but where it is having the four cycles here, four fused ring here. You can see the structure of this where it is A, B, C, D. There are four rings are fused together. So it is called it tetracycline. Four rings are fused together. And where you can see the R groups here. So R1, R2. So by substituting the various atoms or the groups, its name will be different. Like when this R1, R is hydrogen, R1 is a chlorine, then it is chloro tetracycline. The variety of the analogs of tetracyclines, the variety of tetracyclines here. When the R is hydroxy and R1 is hydrogen, then it is oxytetracycline here. Then R is hydrogen, R1 is hydrogen, both are hydrogen here. So where it is the tetracycline. So I'm stopping here. So we'll discuss the remaining part in tomorrow.